Welcome to AI Paper Slop. This is the show where we do a deep dive into the latest AI and tech papers, really breaking them down for the technical listener. And today we are jumping straight into an explicit lower bound for the unit distance problem.
By Will Sawin, yeah.
Right, by Will Sawin. No banter today, just the 60-second summary to get us started.
Mm-hmm.
So Sawin proves there are sets of endpoints in a plane that contain more than n1.012 pairs of points, separated by exactly a distance of 1.
Which is just, it's a massive deal.
It is.
Yeah.
I mean, if you follow computational geometry, you know this completely shatters a famous Erdős conjecture.
Sure.
So an internal OpenAI model recently solved this, working with Li Chen, and it was verified by Mark Selka and Mehtab Sani. But the AI's exponent was, it was explicit.
Right, exactly.
And then a human team stepped in, simplified the AI's work, but the absolute best explicit exponent they could extract was like roughly $6 times 10.
Super tiny. But then Sawin steps in. He sharpens every single step using just incredibly heavy algebraic and number theory, specifically CM fields and the Golod-Shafarevich criterion. And he dramatically boosts that exponent all the way up to 1.0143. Yeah. And he does all of this in a paper the exact same length as OpenAI's original write-up.
Yeah, it's frankly a monumental flex. But to really grasp the magnitude of what Sawin just dropped on the math and machine learning communities, we have to look at the historical baseline of the unit distance problem first.
Wait, because this has been stuck for a while.
For decades, yeah. Mm-hmm. This problem was completely mathematically bottlenecked. So imagine you have a set of endpoints on a flat plane, and you want to know the maximum possible number of pairs of points that are exactly 1 unit of distance apart.
Okay.
Now, the best known upper bound, meaning the absolute maximum number of unit distances you could ever possibly have, regardless of how cleverly you arrange those dots, is a
And it gives us an exponent of like roughly 1.333.
Right.
Exactly. And that upper bound was established by Spencer, Semiretti, and Trotter a long time ago.
Right. But the lower bound, the minimum guaranteed number of unit distances you can essentially force to exist, that's where the real fight has been all this time.
Oh, absolutely. Erdős conjectured that the lower bound was basically just, slightly more than linear.
So mathematically, he framed this as $n plus 0.01.
Right. And for a long time, nobody could decisively prove him wrong. He was just accepted. Then, out of nowhere, an internal OpenAI model disproves it. It proves the lower bound is actually $n plus delta, fundamentally proving that delta is strictly greater than 0.
Which is wild.
It is. The AI's proof was this massive conceptual breakthrough because it found a pathway to prove delta is positive. But like you said, it was completely inexplicit.
Yeah, it just proved the existence of a delta without calculating a usable value.
Yeah.
I like to use it, think of it like a car analogy.
Okay, let's hear it.
Imagine you're trying to prove a car can break the highway speed limit of 65 miles per hour. But your absolute best proof is showing the car moving at exactly 65.0000000, like 30 zeros 1 miles per hour.
Right.
Technically, you beat the limit. You proved it can go faster. But practically, you haven't really solved the engineering problem of making a fast car.
Yeah, that's a perfect way to look at it.
So when human mathematicians tried to clean up the AI's inexplicit proof, they got that exponent of $6 times $1038. It's a microscopic improvement over 1.
Microscopic. The AI found a path through the dark, but it was just this remarkably unoptimized, messy path. And Will Sawin essentially looked at this and decided to, optimize the code.
By completely overhauling the algebraic machinery.
Exactly. He pulls out a practical exponent of 1.0144, which differs from the absolute theoretical upper bound by a factor of less than 24.
So it forces us to ask, right, how do we get from a geometry problem about drawing 1-unit lines between dots on a 2D page to deep algebraic number theory?
Yeah, it feels like quite the jump. But the basic strategy, which, to be fair, Sawin shares with the OpenAI team, relies on moving the problem out of 2D space entirely.
Wait, really? We just leave the 2D plane?
We do. To construct a dense set of points in the real plane with many unit distances, you first construct a highly complex lattice in a high-dimensional space. Yep. Then you project that lattice down to 2D space. The goal is to find a lattice that's just packed with short vectors, where their projections down to the 2D plane all have exactly a length of 1.
Right. So I want to use a shadow puppet analogy here to visualize this projection because it can be kind of abstract.
Go for it.
Imagine you are making a highly complex, multi-dimensional hand gesture. That is your lattice in the high-dimensional space. To the naked eye up there, it looks like a chaotic mess of intersecting fingers. But when you shine a light on it from the perfect angle, it casts a perfect, simple 2D shape on the wall. And because of the sheer complexity of that multi-dimensional hand gesture, there are actually thousands of different ways to cross your fingers in that higher space that will all project that exact same perfect 2D shadow on the wall over and over again.
That's actually exactly what's happening mathematically. In the algebraic architecture of the paper, that multi-dimensional hand gesture lives in a CM number field, which we denote as K.
And CM stands for complex multiplication, right?
Right. A CM field is a totally imaginary quadratic extension of a totally real subfield, which we call F. And here's the mechanical key to your shadow puppet analogy. The squared length of the projection of a lattice vector to the plane always lies in that totally real subfield F.
Oh, I see. And because F is a subfield nested inside K, it inherently has a smaller degree than K.
A significantly smaller degree, yeah. Which directly translates to having fewer elements to work with.
So it's a bottleneck, but a useful one.
Exactly. If you have a massive number of vectors in the larger field K, but their projected length squared absolutely must land in the smaller field F, a collision is mathematically inevitable.
They just run out of room.
Right. Multiple different vectors in K are forced to share the exact same length squared in F. And once you isolate a massive cluster of vectors that all share that identical length squared, you simply scale the whole thing by dividing by that length.
And suddenly, boom, you have generated a staggering amount of vectors in your 2D projection that are all exactly length 1.
You've got your unit distances.
Okay, so the shadow puppet analogy explains how a single projection works. We know what shadow we want to cast, but Erdős's conjecture involves endpoints, where n can scale to infinity.
Right.
How do you guarantee you have enough fingers to cast that same one-unit shadow densely enough to hit that n1 1.0 and lower bound?
Well, this is where we bring in the pigeonhole principle operating on the class group of the field.
Okay, pigeonholes.
Yeah. If you want to show that many elements have the same norm, meaning the same projected length, you essentially sort them into pigeonholes defined by the class group.
Got it.
If your subfield F has a vast number of small prime ideals that split in the larger field K, and the class number of K isn't too large, well, you inevitably pack many vectors into the same pigeonhole. They share the same norm, generating your unit distances.
So if you're a listener wondering why the AI's original math was so inefficient, like yielding that microscopic $10 number, you have to look at how it handled these pigeonholes.
Oh, the AI's approach here was rough.
Yeah, the AI made a mathematically lossy choice. It forced the embedding of an optimal fractional ideal into a principal ideal.
Which is just brutal for efficiency.
Right. So for an ML engineer listening, think of a principal ideal like trying to pack a shipping container using only standardized, perfectly cubic boxes. You're going to have a lot of wasted empty space between those boxes.
Lots of gaps.
Exactly. That empty space is your mathematical loss, your inefficiency. But a fractional ideal is much more flexible. It's like using custom-shaped boxes that perfectly fill every single millimeter of the container without any gaps.
Right. And the AI's requirement to force everything into a principal ideal was this massive, totally unnecessary bottleneck. He simply drops that requirement.
It just gets rid of it.
Yeah. Instead of just using the ring of integers as a lattice, he works with any fractional ideal. This custom fit approach immediately makes the pigeonhole argument far more efficient because no space, or in this case, no vector density, is wasted.
He doesn't just change the type of ideal, though, does he? He also swaps out the container itself by changing what kind of class number he's pigeonholing into.
Yeah, he uses the relative class number instead of the standard class number.
Which is what, exactly?
The relative class number is the ratio of the class number of the CM field K to the class number of its totally real subfield F.
Oh, okay, so it's a ratio.
Right. And this value is significantly smaller. Sawin relies on a specific mathematical bound by Louboutin to tightly control it. By using a smaller relative class number, your pigeonholes are much tighter.
So you are mathematically forcing a higher density of vectors to share the same length.
Exactly. And furthermore, Sawin introduces this specific parameter, denoted as ACLPD, which allows him to take custom powers of prime ideals.
Because, if I remember correctly, the AI required prime ideals to be split over the rationals.
Yeah, it did.
And that meant the AI could only use primes that split in a very specific field extension, and the smallest primes in that kind of extension are typically astronomically large.
Which, again, kills your efficiency.
Right. So by using the KPP parameter and fractional ideals, Sawin gets to bypass that entirely.
He squeezes maximum mathematical leverage out of far fewer, much smaller primes.
So we now have the mechanics to generate a hyperdense cluster of unit distances for a specific set of points. But like you mentioned earlier, we need this to hold for n points where n scales arbitrarily large.
Because a single field configuration will eventually tap out.
It will. To keep scaling again, we need to build an infinite sequence of these fields.
Okay, so we need an infinite sequence, and we simultaneously need to keep the discriminant of the fields small to prevent the class number from blowing up. Because if it blows up, it ruins our tightly packed pigeonholes.
Exactly.
The only way to get an infinite sequence with a controlled discriminant is to create a sequence of fields with growing degrees. And Sawin achieves this using the Golod-Shafarevich construction of two-class field towers of quadratic fields.
Which is just a gorgeous piece of math. The Golod-Shafarevich construction is a really profound tool in algebraic number theory. It provides a criterion to mathematically prove that a specific Golod group is infinite.
Okay.
And if the Golod group of this tower is infinite, it guarantees that there are infinitely many distinct fields layered on top of each other in the tower. That is what allows n to grow without bound.
Wait, hold on, though. If you're building this infinite tower of fields, aren't you going to run out of small primes? Like, if you start with small primes in the rational numbers, their inertia degree, meaning the residue field extension degree, is going to balloon out of control as you go at the tower, right?
Yeah, it would.
And if the inertia degree blows up, the primes effectively become massive, and you lose all the efficiency you just gained from the fractional ideals. Doesn't the math basically start to collapse under its own weight as the tower gets higher?
That is the exact threat to the entire proof. And it is the primary hurdle Sawin had to, engineer his way out of.
So how does he fix it?
To prevent the inertia degree from blowing up, he modifies the tower construction. He takes the Golod group and explicitly quotients it by a fixed power of the Frobenius element for his chosen primes.
Oh, wow.
Yeah, by quotienting out the Frobenius element, he is mathematically forcing the inertia degree to remain bounded no matter how high the tower grows.
But wait, quotienting out the Frobenius elements is essentially adding new relations to the Golod group, isn't it?
It is.
Is this basically like playing a massive, infinite game of Jenga? You are pulling out structural blocks, adding relations to keep the tower thin so the inertia degree stays small.
Right.
But if you pull out too many blocks, you add too many relations, the Golod group becomes finite, the tower stops growing, and you completely fail to prove the theorem for arbitrarily large n.
The Jenga analogy is perfect for understanding the tension here. You are deliberately compromising the structure to keep it thin, and the Golod-Shafarevich criterion is the specific mathematical law that tells you exactly how many blocks you can pull without the tower toppling.
Oh, that makes sense.
Right. The criterion hinges on a strict inequality regarding a pro-Piber group. It says the group remains infinite if the minimal number of relations, let's call it $3, is strictly less than or equal to the minimal number of generator, squared divided by 4.
So $2 has to be less than or equal to $244.
Exactly. Sawin meticulously calculates the exact number of relations he is adding when he quotients out the Frobenius elements. And he proves that the ratio of relations to generators stays safely below that 244 threshold.
So the Golod group remains infinite, the field tower grows forever, and the inertia degree remains small.
That's brilliant.
The theoretical machinery really is brilliant. We have the high-dimensional lattices in CM fields. We are packing fractional ideals tightly using relative class numbers. And we have this infinite Jenga tower of fields balanced perfectly by the Golod-Shafarevich inequality. But, a framework is just a framework until you run the numbers. Let's look at the actual computational parameters, the slop, if you will, that Sawin plugged into this machinery to output the specific exponent of 1.0144 dols.
Right, let's get into the slop. Sawin defines two specific, highly tuned sets of primes to populate this architecture. First, a set called T, which consists of exactly 13 odd primes.
Okay, 13 primes.
Yeah, they are 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, and 43. But there is a crucial structural requirement here. Exactly 7 of these primes. So an odd number must be congruent to 3 modulo 4.
Wait, why does 3 modulo 4 matter mechanically? Why can't he just pick any small primes?
Because the parity directly affects the sign of the discriminant of the quadratic fields at the base of the tower. Having an odd number of primes congruent to 3 modulo 4 guarantees that the quadratic extension behaves correctly regarding its real embeddings.
Okay, so it stabilizes it.
Yeah, it ensures the field is totally real where it needs to be and unramified at the infinite places, which basically prevents the Golod-Shafarevich relations from breaking down. It's the chemical binding agent that keeps the base of the tower stable.
Got it. And then there's the second set of primes, which contains 22 primes in total.
Yes. Square includes primes starting at 2, 3, 5, all the way up to 179, and the internal structure of square is split. The 10 smallest primes in the set are explicitly ramified in the quadratic field, while the 12 largest primes are inert. Sawin pairs these prime sets with a global radius parameter, $3, set to $72. Finally, he assigns highly specific weights, that KP parameter we mentioned when discussing the tight pigeonholes, to every single prime in square weight.
Yeah, looking at the paper, he leans heavily on the absolute smallest primes. For example, he sets the weight for the prime 2, KK, all the way up to 50.
Wow, yeah.
But way at the other end of the set, for the prime 179, the weight KH at $179 is only set to 6.
Right. He is computationally squeezing every last drop of leverage out of the smallest primes to keep the overall norm as tight as possible. He only utilizes the larger primes with smaller weights to satisfy the structural generator-to-relation ratio that's required by the field tower.
What's incredible about this final section of the paper, though, is Sawin's outright admission that these parameters are not even fully optimized.
No, they aren't.
Like, he didn't use a massive supercomputer to find them. He used analytic number theory, combined with a relatively simple Sage script, to search for a combination of primes and weights that satisfy the Golod-Shafarevich inequality and yielded a decent exponent.
Which is wild when you think about it.
It is. For the ML engineers and computational researchers listening to this deep dive right now, he is effectively handing you the keys to a perfectly optimized mathematical engine and saying, the weights I used are just plug and play.
Yeah.
There is massive room right now to computationally search for even better parameters for the prime sets, the radius, and the weights to push that 1.015 in the hour exponent significantly higher.
It really is an open invitation for aggressive computational optimization. However, it is vital to understand the hard mathematical limits of Sawin's specific algebraic architecture here.
Oh, right.
We know the absolute upper bound for unit distances, proven by Spencer, Simoretti, and Trotter, is roughly 1.3333 thousand. But Sawin outlines in Proposition 15 of his paper that this particular number theoretic method has its own much lower theoretical ceiling.
So even if a listener, like an engineer, writes the ultimate optimization script, finds the perfect set of primes, and perfectly balances the Jenga tower, what is the hard cap on the exponent?
Even if you assume a mathematical fantasy-like, the absolute best-case scenario where the relative class number hits the trivial lower bound of 1, like the absolute maximum exponent this specific architecture can ever yield, is approximately 1.242955.
Wow. Wait, really? So even running at theoretically perfect efficiency, we are fundamentally capped well below the ultimate 1.33333 upper bound.
Yes. We are. To break past that $1.2433 ceiling, you cannot just optimize Sawin's parameters. You would need an entirely new mathematical approach or a profound generational breakthrough in how we bound relative class numbers.
Like what?
Like something probably conditional on proving the generalized Riemann hypothesis.
Oh, wow.
Yeah. For this specific algebraic framework, 1.242955 is the absolute finish line.
Which really leaves us with a fascinating dynamic. We started with an internal OpenAI model finding a brilliant, highly novel pathway in the dark to disprove a decades-old Erdős conjecture.
Right.
But it left a massive efficiency gap because it didn't really understand the nuance of the math it was using. It took a human mathematician, Will Sawin, to step in and pave that path efficiently using elegant, deeply human tools like fractional ideals, relative class numbers, and the Golod-Shafarevich criterion.
It absolutely highlights the current frontier of AI in advanced mathematics. The models, they excel at structural exploration and finding the existence of a path. But human intuition is still required to understand the deeper algebraic geometry required to actually optimize it.
Which leaves you, the listener, with this to think about. What happens to mathematical research when we start explicitly training AI models on these highly optimized, human-refined algebraic techniques?
That's a big question.
When an AI natively understands why embedding into a principal ideal is a lossy bottleneck, and it automatically reaches for a fractional ideal instead, will the next AI-generated proof hit that $1.244 size ceiling on its very first try?
That is the real frontier this paper points toward.
Thanks for joining us for this deep dive into the math. We'll see you in the next one.